for it. Okay, it's first time to proceed practice session on the diffusion model in programming for AI class. So during or after this class, please leave me any kinds of comment for getting this material better. So we'll go over original DDPM paper by Jonathan Ho, implementing it step by step in PyTorch based on the implementation of Phil Wang, who has another name of Lucid Lanes. Okay, all right. And about the reference, I think this is the most educative. I mean, the annotated diffusion model material is the most educative tutorial for DDPM, and most of contents in the notebook file you are now looking at are heavily borrowed from this tutorial, and I really owe them. Okay. But there are way too many modules in this tutorial, so I quite compilated this tutorial. Okay, the whole picture first. There are a bunch of modules in this tutorial, so I summarized the flow in the figure. Sorry, bracket. Okay. I summarized the flow in the figure, and you guys are already, I mean, the Professor Edward Choi already covered the theoretical parts of this class, but let me recap. First, so you guys are you guys already familiar with DDPM? Frankly speaking, please. So is there anyone who totally understand the forward diffusion process and reverse diffusion process in DDPM? Anyone who totally understood what Edward Choi lectured? No? I didn't mean that the answer. I just want to know how much you guys understand the DDPM material. Tani. Okay. Some guys sent me DMs. Okay, and maybe many of you guys do not totally understand the material. Roughly understood. Okay. I think just a base. Okay. So and then let me briefly recap the theoretical part. Okay. But this figure is for explaining the module in this specific module in this practice session material and its meaning in the original DDPM paper. So at first, at the early stage, sample 3 things, which are x0 from original or real data distribution, and sample t from a uniform distribution with interval 0 to interval from 0 to max time step large t, and lastly, sample epsilon from standard normal distribution. Until now, it's okay, right? And next step is forward diffusion, which simply means making noisy data with 3 elements we already sampled. This is done by QSample function in this material. I mean, the material means the notebook, this IPython notebook file. And this is done by QSample function. And we can control how to schedule to add noise with data. Okay, and be careful, there is no learning process in for diffusion. It is already predefined by the for diffusion process is already predefined by beta. We can schedule the for diffusion with the parameter beta. So there is no learning process. For diffusion simply means just making noisy data with the 3 elements you already sampled. Okay. Okay, then our noisy data go into UNet, which the original DDPM authors employed for their backbone. And at the early stage in the UNet, in this yellow shaded UNet, I mean the before applying operation of convolution to the X noisy, we embed the time step information with T. This makes this time embedding layer makes the network know at which particular time step it is operating. We only use time information in this tutorial, but you can use same embedding structure for class conditioning. For example, in the MNIST dataset, the picture of 0 is labeled by 0. So if you condition the picture of 0 by the number 0 in this embedding layer, then you can choose to generate the synthetic image of picture 0 at the inference stage. Okay. Till now clear? Is it clear until now? Because this is basic flow or logical flow in the DDPM. So if you don't understand this, at least this material, this figure, then you will get lost. Feel free to bother me if you don't understand what I said. So is it clear until now? Okay. Okay, after embedding process, the noisy data goes through downsampling layers and bottleneck layers and the upsampling layers in order from here to here, like any other autoingress structure. Then consequently, UNet outputs the predicted noise tensor, which means the UNet with parameter theta predicts the noise we already sampled at the early stage. Right? Simply speaking, this UNet tried to predict this one by parameter theta, and we have to close the gap between this original data already sampled and predicted noise using loss function. This is the whole process of training shaded by green. I rather use this annotation system. Good. Okay. So sample 3 elements, and by using these 3 elements, make noisy data with 4 diffusion parameters by beta, and pass it through the unit with specific embedding, which let the model know the time step. Then unit ups the predicted noise, epsilon theta. Epsilon theta. And we have to close the gap between these two, epsilon theta and real epsilon, with loss function. Cool. Okay, what I've described build the training process of model, which is shaded by this green area. And okay, let's go into inference stage. Let me zoom in. And you start from the zoom in more. Okay. You start from the total isotropic noise and denoise this noise step by step with reverse diffusion process toward clean image of cat. We can take a single step reverse with, this rightward arrow means, this rightward arrow is implemented with this p sample function in this notebook file. And as you see, these all images draw a trajectory from total noise to real image. Not real image, plausible image. And p sample loop function outputs this trajectory. And this p sample loop function is just for making GIF file for our session. So if you're employing DDPM, if you're trying to employ DDPM into your research, just throw it away. Okay. The point is the denoising process, which is equal to reverse diffusion, is done by step by step in a step by step manner. Unlike the training process. In the forward diffusion process, you can do quantum jump to from 0 to specific time step t, but in the reverse diffusion process, you can just reverse just a single step. So we have to go through total large t steps, large t reverse diffusion step. Okay. Any question till now? No question. By the way, it can be confusing, but this epsilon this epsilon theta Okay, let me discuss this epsilon theta. Does it mean the noise added during total, I mean, you know what, do you know what this is for? First, this is noise from 0 to t. Second, noise for a single time step. Quiz. The answer is 1 or 2. Please answer it in the chat box. What's the answer? 1 or 2? First, the answer 1 is noise added to the data during the time step 0 to t. Second one is this is just single noise for a single time step. 1, 1, 1, 1. So all you guys think this epsilon theta is for predicting accumulated noise from 0 to t, right? Right? No, actually it's not. The answer is 2. But it will be clear that, wait a second. But as you see the next part, you will get naturally what I said. So let's just move on. But please remember that this predicted noise is for predicting the added noise for a single time step. That's why we have to go. We can't just reverse a single time step in the reverse diffusion process. If we can accumulate noise in the training part, if our unit model can predict the predicted, sorry, if our unit model can predict the accumulated noise added to data, then we can do quantum jump from this isotropic noise to this real image, this plausible image, but we can't. That means we should go through this reverse diffusion step in a stepwise manner. So that means this predicted noise is for a single time step. 한국말로 다시 설명을 드리면 저의 이게 많은 분들이 헷갈리고 계시는 것 같은데, 그러니까 진짜 빠르게 스킴을 하면은 리얼 데이터 디스트리뷰션에서 데이터 하나 뽑고 t 타임 스텝 중에서 t 뽑고 그 스탠더드 노멀에서 입실론 뽑고 해서 이 세 개를 가지고 잠시만요. 오케이, sorry. 이거 세 개를 가지고 포워드 디퓨전을 통해서 여기서부터 이런 노이지한 데이터를 이렇게 만들어주는 거죠. 그리고 그 만드는 과정이 베타라는 파라미터로 통해서 스케줄링 될 수가 있고, 근데 이 노이지 데이터를 윤에 통과시켜서 우리가 하려는 바가 뭐냐라고 했을 때, 그럼 그거는 결국에 그 노이즈를 프리딕트 하는 건데, 이런 유닛이 있으면은 그 노이지 데이터를 넣어서 입실론을 예측을 하는 건데, 이 입실론이 예측하는 바가 무엇이냐라고 한다면은 우리의 트레이닝 오브젝티브인 로스를 봤을 때 이거와의 갭을 줄이는 거란 말이죠. 얘랑. 그럼 이 입실론 세터가 예측하는 게, 즉 이 입실론이 그러니까 의미를 하는 게 1번 accumulated 0에서부터 t까지 accumulated 된 로스다. 노이즈다. 2번 그냥 뭐 예를 들어서 t-1에서 t로 갈 때 더해진 싱글 타임 스텝 노이즈다 라고 물었는데, 저는 근데 여러분들은 지금 다는 아니고 1번이라고 답을 하셨는데, 사실은 답이 2번이다 라는 거고, 만약에 저희가 이런 accumulated noise를 잘 예측할 수 있었다면 리버스 디퓨전에서도 이렇게 싱글 타임 스텝씩 갈 필요가 없이 그냥 한 번에 여기로 퀀텀 점프를 할 수 있었겠죠. 근데 우리가 그럴 수 없는 거잖아요. 네. 근데 이게 지금 머테리얼을 좀 더 보다 보면은 이해가 될 거니까 일단은 넘어가겠습니다. Okay. Okay, what is a diffusion model? Okay, as I already said, the theoretical part was already covered by Professor Edward Choi, though, but I will briefly cover it again. A diffusion model is a neural network learns to gradually denoise data and predefined, which means that there is no learning process. Predefined for diffusion process Q adds Gaussian noise to an image until you end up with pure noise. So this way is forward from mirror image to total noise, and learned reverse denoising diffusion process where a neural network is trained to gradually denoise an image starting from pure noise until you end up with an actual image. So this is reverse, this is forward. Cool. In more mathematical form. More mathematically speaking, we can sample, we can sample x0 from real data distribution qx0. We can sample by this notation. Okay. Sample real image from real data distribution qx0. And in forward diffusion, we corrupt the x0 with specific meta scheduling. As I already said, the forward diffusion process is parameterized by the beta, and we can control how to corrupt the image but with the parameter beta. Then we can parameterize xt as conditional Gaussian distribution like this. And okay, is it okay? The meaning of, where is it? let me zoom in. The meaning of this equation is the noisy data for next time step is somewhat weighted sum of previous time step data, previous time step noisy data, plus a noise, plus the new noise for this time step. Okay, this is just coefficient like for weighting these two. 그러니까 이번 타임 스텝에 특정 비율로 이번 타임 스텝에 특정 비율로 노이즈 더한다. 그 비율을 정하는 게 베타다. 그래서 다음 스텝 노이즈 데이터를 만든다는 거죠. 여기까지는 이제 된 것 같고, 이제 여기까지 됐나요? 괜찮나요? Are you okay? You okay, guys? 여기까지 이제 설명이 된 것 같고, 리버스에서 예측하는 게 싱글 타임 스텝이라는 걸 이해를 못 하신 것 같은데, okay? And we leverage a neural network to approximate this conditional probability distribution, and let's call it p zeta x t minus 1 given xt. T minus 1 to t. If some noisy data has larger t, then it means that it is more noised, right? More noised. So if you go from t to t minus 1, then it means denoise, right? So xt minus given xt means go from xt to t minus 1. So this means denoising process, which is parameterized by theta in our UNet neural network. Okay. And the model and our neural network model, the Gaussian distribution which is parameterized by defined by two parameters. One is mean of it, and the second one is sigma, the variance of it. So we can parameterize the process, the reverse process as p theta, as I already said, and this is a conditional normal distribution which can be expressed in this way. This is the whole learning process, and which consists of words and cluster gap between noise with the loss function. Okay, next step is object. I simply explain the laws by this for character, but let's go further. For further detail, please look this part. We will build the laws using variational lower bound or elbow. variation of urban elbow. And during the optimizing the loss, we can jump the time steps for diffusion, since I'm explaining this part. During the optimizing the loss, we can jump the time steps for diffusion, since sums of Gaussians is also Gaussian. There's real image, and we forward it to, how can I say, total noise. And this, all the steps in the forward diffusion process are done with conditional Gaussian distribution, which is already Gaussian. So Gaussian, this leftward arrow means Gaussian. So sum of Gaussian means Gaussian. Sum of Gaussian result in Gaussian. So we don't have to go through the forward diffusion process in a stepwise manner. We can jump at once, not this way, from 0 to time step t. That's what I'm explaining here. Okay. And question. 리버스 디퓨전은 리버스 디퓨전은 1에서 2스텝이든 99에서 100스텝이든 동일 네트워크. The 승민 asked, like, do we use same neural network? I mean, do we use same pre-trained unit for all the reverse diffusion process at any time step? And the answer is yes. Then how can the model knows whether it is time step 0 or time step 99? That's your question, right? The model, as I already covered here, the point is this time MLP. This embedding is for time conditioning and class conditioning. And this time MLP layer makes the network, I mean our neural network, total neural network unit, know at which particular time step it is operating. So if you add t equals 0, if you input the t equals 0 into time MLP layer, then it produces an embedding for letting the unit know the time step 0. So this unit can know the difference by this embedding for time step. Cool. You're right, 승민? 그러니까 승민님의 질문이 되게 좋은 질문인 게, 이거 어떻게 줘? 알겠다. 그러니까 이 유닛을 그러니까 디노이징을 할 때도 100에서 99 가는 거랑 1에서 0 가는 거랑 뭐 2에서 1 가는 거랑 똑같은 유닛을 쓰냐는 거잖아요. 그게 다 똑같은 디스트리뷰션 노이즈를 프리딕트 하는 걸 또 아닐 텐데 왜 똑같은 걸 쓰냐. 그러니까 그거를 그 타임 스텝을 구분해 줄 수 있는 게 이 타임 임베딩이라는 거예요. 똑같은 파라미터를 쓰되 우리가 매번 그 노이즈 데이터를 만들 때 타임 MLP로 임베딩을 해주니까 모델이 어느 타임 스텝에서 그 디퓨전 프로세스를 하고 있는지, 그러니까 노이즈를 프리딕트 해야 되는지 알 수 있다는 거죠. 똑같은 파라미터를 쉐어하더라도. Okay, let's move on. There's a lot of remaining stuff to cover. Okay. Okay, wait. Actually, by using this quantum jumping, this by using this property, I already said we can jump to specific time step t, right? And with this nice property, we can reparameterize or change the training objective to this from this. Originally, the DDPM predicts the mean of Gaussian, but by using this nice property, we can change it. We can reparameterize the training objective to let the model predict epsilon, and this one works better. Okay, that's why we call this property as a nice property. Cool. Okay, training process. I said a bunch of things like this, but these 6 lines of our algorithm says everything. Sample 3 things and make noisy data, and by using it, predict epsilon theta. This is noisy data. This equation is for parameterizing noisy data, and these two have same meaning, and cost gap using gradient descent, and that's all until the model converges. Done. Cool. So again, this is the last chance to question. If you don't understand anything about this scheme or this figure, please ask me now. If you want to understand DDPM, I will wait for 10 seconds. Okay. By the way, we have many sections, but the point is, please don't get lost. The point is, where is it? Where is it? Oh my God. Yeah, the point is this for diffusion process and sampling, which means adding the process for adding noises and denoising process. So these two processes are the novel and important part in the original DDPM paper, and anything else are already given to them. So don't get lost. Only these two are important. Okay, let's get started. We implement this neural network step by step. And okay. If you think it is not novel part, if something is not novel part of DDPM paper, then just push the shift enter and run it. This section is for just importing the packages, run it. And next cell is for network helpers, and these functions or classes are used often by Phil Wang, Lucid Lanes, that's running. And positional embeddings. And as I already said, it makes the network, it makes our unit know at which particular type step it is operating for every image in a batch. Okay, running. Next step is the unit model is highly modularized, and you can choose ResNet or ConfNext block for our unit, for building our unit model. And in the original DDPM paper, others employed a wide ResNet, but Lucid Lane decided to also add support for a ConfNext block. And just run it. Attention model. There was a transformer class in our program for AI class, right? So, oh, sorry. There are two kinds of attention. First one is regular multi-head self-attention and original transform paper, and second one is linear attention. And the difference is time and memory requirements. First one has quadratic scale. The second one is a linear scale. It's about it's about the model efficiency, right? But this is not for a class. This is not a class for attention. So just run it. Group normalization. DTPM models interleave the convolutional and attention layers of the unit with group normalization. And this will be a single block for our unit, and just run it. This is conditional unit, which is employed in our DTPM scheme. This shaded by yellow. But unit is not the novelty of the DDPM paper, original DDPM paper. They just employed unit, and as I recall, there is no specific reasons to choose unit as their backbone, but I think unit is a go-to options for building an encoder. So maybe that's why they choose the unit for their backbone structure. So this is conditional unit built with the building blocks, ResNet, ConfNext, and attention module. Yeah, ResNet, ConfNext, and group normalization, attention module, residual connection, upsampling operations. That you already built. Okay. So define the class just by running it. Okay. This is fourth diffusion process, which is important in the original DTPM paper. So, but this block is for just scheduling. As I already covered, you can schedule the fourth diffusion process. I mean, the fourth diffusion process is predefined, which means there is no learning process, right? And for diffusion is predefined by beta. We can schedule the for diffusion process by beta with the parameter beta. And this section explain it. We can use various beta or various form of scheduling. For example, cosine scheduling, linear scheduling, quadratic scheduling, sigmoid scheduling. But the point is, this shape, the fourth diffusion process, which adds the noise to real data, consists the shape and the value beta. So simply, this is just for designing the process of adding noise to real data. Just run it. And maybe there will be a quiz now. Okay. The time step t is also hyperparameter, for example. Oh. 아이패드가 왠지 for example, this is real image x0 and total isotropic Gaussian noise xt. This is total noise, and we split this trajectory with time step t. If you choose a small time step, like 4 or 5, the model have to go through this trajectory in 4 time step. But if you increase the time step, then the model can easily learn the reverse process by splitting the whole trajectory as to many bunch of time steps. But as you increase the time steps, max time steps, the training time and inference times will increase either. So that's the problem of the chronic problem of the diffusion model scheme. Anyway, what I want to say is time step is a parameter, hyperparameter. You can choose it. So there was, in a mathematical form, there was many argument like symbol like beta, alpha, alpha, and Q and P. And this word process this block defines the alpha, scheduling alpha, the beta and alpha. But the point, but don't get lost because alpha is another form of beta because alpha t is divided by 1 minus beta t. So alpha t is the role of alpha t is just for designing the full diffusion process like beta. So it has same meaning. Don't get confused. Just run it. Oh, this is number. Run it. Run these 2 blocks, and this is your case. Q sample. This is for diffusion process, and there is Q sample function here, and its input is xstart, means original image, which means original image, and a specific timestamp t, and sampled noise from standard normal distribution. And what we have to do is outputting, let this QSample function output the X noisy using these 3 elements. Okay? And maybe you will need X equal, no, very simplified. Oh, where is it? Oh. By using mathematical by using the nice, so-called nice property, we can simply parameterizing that word diffusion process, but there is no, where is that? I will find it from original DDPM paper. Denoising diffusion processing. Hold on. Where is the word diffusion? 혹시 입실론 세타, 그러니까 여기서 하려는 게 뭐냐면 이 QSample에서 in this QSample function, what you have to do is outputting X noisy using X0 and T and epsilon. But I want to give you a mathematical notation to help building this return object. But I can't find it, but if you can't, please try it for 5 minutes. While you are solving it or coding it, I'll give you the figure that you can get a help from. Okay, code it, this part. Oh, it's already. Oh. If you have any question, just feel free to ask. Oh, you can refer this equation. What you have to do is outputting this term. Okay? Because our unit is basically our inputs of unit is basically xt and t. What? Xt and epsilon. So this means xt and this means t. And to build xt, we need x0 and t. Like these three elements correspond to these three, and we want to build 4 diffusion process in a quantum jump manner. So please let this QSample function output this term. Square root alpha's cumulative product t means this one, and square root 1 minus alpha cumulative product t means this one. And you already got x start and t. No, epsilon. Noise. So by combining these 4 terms, construct the return. It's already 11:41, so if it gets to 11:45, then if you have any kind of a schedule or plan, then feel free to go out. Still, feel free to reach me or upload something in the chat box. This is okay. It's 42, 11:42. So this is linear combination of x0 and epsilon, right? By weighted by square root alpha comprod and square root 1 minus alpha comprod t. So the answer is this one. The linear combination of this x start and noise, but weighted by these two terms. Okay. Next step. You have to, you have to fill this blank in P lossless function. And the objective of this P loss function is close the gap between this real already sampled epsilon and this epsilon theta, which means predicted noise by unit. So you have to, this will be this will be the sum of output of Q sample function, and this will be the output of the unit model, which is named by denoise model in this argument. Fill the blank, please. This should be Q sample, blah blah. This should be this denoise model, blah blah. And fill the argument. Till 11:48. Q sample for some guys who need more explanation. Q sample had the inputs argument of Q sample function is this one, right? And the input argument for denoise model, which is unit, instantiated by unit class, is, where is it? Unit, please, neural network, in neural network session? No. Look at this. Forward function, forward method in the unit class, which will be instantiated into into our denoise model. So delete the self, and the argument for this denoise model, input argument for this denoise model should be x and time. And please match this target input argument using this variable. I mean, rephrase this argument using this. Algorithm 1에서 in algorithm 1, the objective is xt에서 x0으로 리버스 할 수 있는 입실론을 배우는 건가요? 알고리즘 1. 아까 그거랑 똑같은 것 같은데. 그러니까 제가 아까 the question of Junhyun is in algorithm 1, the training objective means that does the training objective means the learning epsilon that can reverse the noisy data from xt to x0? And the answer is no. And your question is, and I already asked you guys, choose between 1 and 2. First one is accumulated. Second one is single time step. What is the epsilon for? I already questioned this, and Junhyun's questions means, is 1 is correct? But the answer is 2. Let me explain why. I didn't explain it fully. This is x0 and xt. This is xt, and there are many time steps scheduled by beta. And your question is, this epsilon zeta is for jumping from xt to x0. But my answer is no. Why? There is many epsilon for each time step. There is time step 1, 2, t-1, large t-1, t. And for each time step, epsilon is sampled. Epsilon. And all these epsilons are sampled from standard normal Gaussian distribution. But all these epsilon are differently instantiated. Okay? And the objective of this epsilon zeta is predicting each epsilon zeta. And how does the model knows each time step? How the models know the difference between time steps? By, as I already said, time embedding. Clear? So all this epsilon do not mean the accumulated epsilon. These are all of each this epsilon means the sampled noise for each time step. Okay. So this should be, this extract and T and noise should be extract and T and noise, right? And the second one, this X. What should be this X? X noisy. And time should be T. You can skip this argument. This. The answer is, this is the answer. Because our unit's input is X noisy with T. So you have to input this X noisy you already built and T for our denoise model, which means instantiated unit model to predict the noise for each time step. Okay? Okay, let's go next. Please, this is for defining a PyTorch dataset and data loader and pre-processing process for image dataset. So just run it. Where did I miss? Just run it. This is all these are for just pre-processing and preparing the dataset for training. So run it. And there are two more questions. The P sample is running out of time, so I really wanted to feel the answer now, but it will be really helpful to you guys if you fill the blank your own answer with your own answer. So P sample means the single step of reverse diffusion. What you have to do with this P sample function is as I already said, a single time step of reverse diffusion. And to do that, what should be filled with these question marks? Let's fill it until the 12 p.m. Okay, for more information, I bring the equation 11 in the paper and algorithm 2, line 4, this equation. So all you have to do is implementing this one and this one. Let me zoom in. This one, this one. Okay, it's noon. What's the model mean? What is our predicted model mean? Square root reciprocal alpha t parenthesis xx minus beta t divided by square root 1 minus alpha t compra t multiplied by model predicted noise by model. This is predictive model mean. And second one is model mean plus model mean. Model mean plus square root posterior variance of t multiplied by noise. Okay. Okay, and if you fill the blank properly, then just run it and train the model. But now it is already 12:02, so if you wait until the training done, then you miss the lunchtime. And so I will show you the results first. By this figure, it seems like the model is capable of generating a nice t-shirt. We start from, wait a sec. We start from total noise like this, and it gradually becomes to some t-shirts, right? This GIF figure iterates the time step, reverse time step in a reverse way, right? Shows the reverse diffusion process. If this figure shows the whole reverse diffusion process. Okay. I will upload the solution for this IPython notebook, so don't worry about it. And there are really bunch of papers and articles, project pages for follow-up more reading material. Maybe you guys heard about the stable diffusion, and the stable diffusion employed this scheme, which is named by latent diffusion model. Latent diffusion model. And the DDPM is I think it became the standard in the diffusion model domain. So if you want to study more in the diffusion model, about the diffusion model, then just start from the original DDPM paper written by Jonathan Ho in 2020. Every other papers employed the mathematical notation used in the original paper, the original DDPM paper. So if you want to start, please fully understand what DDPM said, the original paper DDPM said. Okay, and these two blogs, the Yangsong conducted research about the score-based model, and he at the early stage he didn't know about the relationship between score-based model and diffusion model, the denoising diffusion model, but at the DDPM paper, Jonathan Ho proved the inherent relationship between score-based model and diffusion model. So, inspired by that, Song integrate the diffusion model scheme into score-based model, and that's the flow of in this domain. And so this Yang guy is a pioneer in this domain. So please read it. This will be really helpful. And Lilian Wang, I don't know how to read it, but Lilian Wang's blog will be helpful either. 오케이. 혹시 노이즈를 여러 번 샘플링해서 리버스 해보면 okay. Junyan's question is if we sampled total isotropic Gaussian noise and if we denoise that total noise, can you get any other images like shoes or dress, one piece in the fashion MNIST dataset? The answer is yes. And if you want to target a specific class, then you have to add the class conditioning module like time MLP. The name will be, well, for example, class MLP. And by training that, you can conditionally generate the images with specific for the specific class in the dataset. Okay, this is the end of the practice session. And as I already said, this is the first time to proceed the practice session in this programming for AI classes. So please leave me any comments to improve this material better. So, and this is the, okay, class dismiss. If you have any question, I will wait for about 2 minutes. And if you have any question, feel free to let me know. Okay, bye-bye.